All right, chapter 25, part 2 is all about hypothesis testing for paired samples. So like we've seen with all of our other hypothesis tests, we should have two different hypotheses, our null hypothesis and our alternative hypothesis. For the null hypothesis, we are going to assume that the two samples have no difference. So we would write that as mu sub d, that's the true average difference, is equal to 0. We have a couple options for our alternative hypothesis. The average difference could be greater than 0, or the average difference could be less than 0, or the average difference could be not equal to 0. A couple refreshers on those formulas. When we're going to find our standard deviation, we take the standard deviation of the differences and divide by the square root of n. We will eventually be finding a test statistic, so a t-value. To find that t, we're going to take our average differences, so that's d bar. We will subtract 0. We're subtracting 0 because our true mean we're always assuming to be 0. And then we will divide by standard deviation, which is whatever we get over here. All right, example 1 says, is there a significant difference in calories between servings of strawberry and vanilla yogurt? Based on the data shown in the table, test an appropriate hypothesis and state your conclusion. The first thing that I would do is always take a look at your data and really think about whether this data is paired or whether it is independent. So at first glance, it looks like we definitely have two samples. We have some data coming from strawberry yogurts, and then we have data coming from vanilla yogurts. But the way that it's presented to us is that each of these numbers are coming from the same brand of yogurt, so this data is definitely paired. That's an important first step. Make sure you don't skip that and assume because there's the same number of data pieces in each sample that it is paired. You really need to think about whether these numbers have something in common. From here, we want to use our calculator, so I'm going to type in strawberry into L1 and vanilla into L2 in my calculator. From there, we want to figure out what L3 is. We're going to use our calculator to find the difference between L1 and L2. So we go up to L3, type in second 1 for L1, subtract second 2 for L2, and your calculator calculates all of those differences for you. We're really going to be focusing on this L3 because I am trying to test something about the differences. I like to stop there and write down my variables, so I'm going to find d bar and standard deviation by going to stat, calculate, one variable stats, make sure your data is pulling from L3. We can then find the average and the standard deviation. I also like to write down the n value, which again I can check by making sure there were 12 brands of yogurt. From here, we are going to test an appropriate hypothesis, so we're still going to use phantoms. Like we've seen in the past, P stands for the parameter. In this case, I really care about the differences, so I'm going to say that mu sub d, so the average difference for the strawberry versus vanilla, and we think that this is the true average difference in, what are we looking at? It looks like this is in calories. Do we have a numeric value for that true difference? No, I'm assuming that it's 0, but what I'm trying to see is if it is different than that. Next up, we have h for our hypotheses, so I know that I will need h sub 0 and h naught. We said in the very beginning here that our h naught is always that mu sub d is 0. I'm going to assume that strawberry and vanilla yogurts have the exact same calories. It looks like I am trying to prove if there is a significant difference. So not necessarily does strawberry have more than vanilla or does vanilla have more than strawberry. I just care about if there's a difference. So this one will be mu sub d is not equal to 0. So this is going to be a two-sided test, which we haven't seen in a while. But remember, with those two-sided tests, we will run this just like a regular one-sided test. Once I have my p-value, I will then multiply it by 2. A in Phantom stands for assumptions and conditions, so I will need to check all of those. Your first two stay the same, so I need to make sure that these were random. I'm not seeing anything in here that says that these were randomly chosen, but I definitely think these 12 brands of yogurt will represent all brands. My second condition is to make sure that my sample is less than 10% of the population. Again, I think that 12 brands of yogurt is less than 10% of all brands. Another condition I need to check is that the differences are nearly normal. So I'm going to go back to my calculator here, going to second y equals for my stat plot. I'm going to jump right away to my normal probability plot. Make sure that you're pulling data from L3. And it's looking a little curved there, but I will say that this is nearly normal. Close enough for us, right? The next thing I need to do is check that my data is paired, which it definitely was. That was one of the first things that we thought of in the beginning. Data is paired. And my last condition is that the differences need to be independent. I definitely think that is true, just because America's Choice has a difference of 10 doesn't mean that that's impacting anything else here. Next up in Phantoms, we have N, where we are naming the test. This is called a paired sample t-test. Again, very nice and easy there. Paired sample because guess what? We have two samples that are paired. And t-test because I'm looking at averages, so I need to use a t-score rather than a z-score. T in Phantom stands for our test statistic, so this is where I look at my specific sample. We found the average difference to be 12.5, so that's what I will use for my test statistic. O in Phantoms is where most of our math comes from. Again, I need to have a mean and a standard deviation. So I'm going to start with finding what I expect to be true for my sample. This comes from your null hypothesis. We assumed that the difference should be 0, so our mean should be 0. When I go to find my standard deviation, we will take the standard deviation from our sample, so the 32.51, and divide by square root of n, which is 12. Let's go ahead and type this in. So 9.38. Once I have a mean and standard deviation, I'm good to draw my model. My mean is at 0, and my standard deviation at 9.38. I need to drop down my test statistic, which was at 12.5. Because this was a two-sided test, we're going to have this shading over here on the right, but then equal distance away from my mean, I'm also going to have a shaded area on the left. We will still start with finding our t-score, so I'm taking my sample mean, the 12.5, subtracting 0, and dividing by my standard deviation. I got a t of 1.33. From here, I'm going to use my TCDF to find that area on the right-hand side. My lower bound is my z-score of 1.33. Upper bound, a very large number. And my degrees of freedom is 1 less than the sample, which there were 12 brands that were tested. So it looks like 0.1052. Because this is two-sided, we will need to multiply this by 2. So in the end, I'm getting a p-value of 0.2104. Okay, M and S, because this p-value is quite large, I am going to fail to reject H naught. So I'm failing to reject this guy up here, which means I think that this is true. So at this point, I do not have evidence to suggest that there is any difference in calories between strawberry and vanilla yogurt. So I will say there is no evidence to suggest there is any difference in average calories in yogurt, in strawberry and vanilla yogurt. Again, there's lots of different ways to say that last sentence, as long as you're saying something along the lines of we don't have evidence to suggest that there is a significant difference between the average calories found in strawberry yogurt versus vanilla yogurt. Go ahead and pause your video, take a minute to try the next one. I will show my answers so you can check, and we'll move on from there. In example 2, you are looking at the average job satisfaction score, so it was before and then after. Before and after they used an exercise break. Hopefully we all got this p-value, just the true average difference in job satisfaction. I personally think that finding the alternative hypothesis can be kind of tricky sometimes, so oftentimes I have to do a little bit of side work here. We are looking to see if it improves job satisfaction, which means that the scores after should be greater than the scores before, so L1 is less than L2. Again, kind of like when we did with 2 samples, when I subtract it over, it shows me that those differences, so my mu sub d, should be less than 0. All of our conditions were met. Your normal probability plot is slightly curved, but mostly straight. After we find our mean and our standard deviation, we should get a very low t-value, negative 3.6, which in turn gives us a small p-value, 0.0029. Because that's so small, I'm rejecting the null, meaning that there is evidence to suggest that this exercise break did in fact improve the average job satisfaction rating.